we are going to do is we are going to gain a deeper insight about the gauge R&R. Initially, I will share my MINITAB screen, explain you how we can actually create the gauge R&R study worksheet, how to actually conduct it. And then once the data is available, we analyze it. And then we will also proceed and look at the graphs one by one and figure out the root of the problem. And then accordingly, corrective action can be taken. So I'm just sharing my MINITAB screen. So please confirm whether my MINITAB screen is visible to all of you.
Visible, sir.
Very good. So yes, done. Thank you. So now you go to stat, you go to quality tools, go to gauge study, and then gauge R&R study worksheet. In case you have a laptop, also the MINITAB installed as advised, you can practice parallelly with me. So this is going to be completely MINITAB based. So I repeat it again. After opening MINITAB, go to stat, go to quality tools, go to gauge study, go to gauge R&R study worksheet. So we need to create gauge R&R study worksheet. So here the number of parts. You remember already we decided that minimum how many number of parts we should select? Minimum is 10.
10 numbers.
Always select 10. And when you are selecting 10, make sure you take 5 on the right side of the mean and 5 on the left side of the mean. Otherwise, 5 on the right side of the target value, 5 on the left side of the target value. Say, for example, you are measuring the metal thickness. Thickness is 10 mm plus or minus 0.5. Then 10 to 10.5, take 5 units. Then 10 to 9.5, take 5 units. Hope all of you understand how to select the 10 parts. Am I correct with my statement? Please confirm or show reaction.
Yes.
Sir, please repeat.
You need to select 10 parts. And you know the product you are manufacturing, you know the customer targeted specification, right? So customer targeted specification is 10 plus or minus 0.5. Now the right side tolerance is 10 to 10.5. Am I right?
Yes, sir.
In that range, select 5 parts. Left side tolerance is 9.5
9.5.
10.
And
In that range, select 5 parts. So you have 5 on the right side, you have 5 on
5
the
on
left.
the left side.
So approximately 50-50. You know why are we doing like this? We are creating normality. Because what is normality? 50% data on the right, 50% data on the left. Am I correct? Normal distribution is symmetrical at the center. All of you
Yes,
agree?
Yeah.
Very good. So now this is that. Number of operator, this is purely based on the situation. If there are too many operators, you can go for 5 or even 10 also here, right? But if you are sure only 3 quality inspectors are there, probably involve all the 3. Right? Probably involve all the 3. And if there are too many, you can use a random sampling technique and choose 3 or 5 or the number of appraisers you want and a random method. So 3 operators selected. Now let me say the 3 operators are, one operator is our Bobin, and another operator is our Rajesh, and the third one is our Sagar Mogit. Right? Sagar Mogit. And 10 parts, 3 operators, replication. Can anybody tell me why should we go for replication? Why are we going for replication?
To understand the repeatability and reproducibility.
Yes. No, repeatability only. The replication is required to check the repeatability.
Okay.
And replication is done to minimize the bias. Ultimately, we want our data to be accurate. For that, our data must be, first of all, precise. Right? So replication can be 2, replication can be 3. It depends, right? The time, because accordingly, the number of experiments will increase. Shall I keep it 3? Yes?
Yes,
Yeah.
sir.
Anyway, it's a 3 number and there will be 1 replicable.
Yeah. Now 10 parts, 3 operator, 3 replication, which means totally you have to do 90 experiments. Let me show you what are those experiments, right? So when I click OK, your data collection sheet is ready. Can all of you see the data collection sheet with run order, part number, and operator name. Look here, there are 90 experiments. All of you, can you see 90 experiments?
Yes, sir.
Yeah, we can.
This 90 experiment is going to be a sample data which your project team is going to collect during the data collection stage. What is your step number data collection? Data collection is step number 6. Data collection plan is step number 4. And GAGE R&R is step number 5. Step number 6, you collect the data and measure the baseline performance. Now 90 experiments will be conducted. The sample will be helpful, will be used to estimate the total amount of error that may populate when your team is actually collecting the data during step number 6. Hope it is clear now. Now the data can be written here. Whatever is the data. So if all of you do some experiment right now and then give me the data, I can just put it here, right? Or otherwise, let me open an existing data file, open worksheet, sample project data. I need the GAGE AI AG, right? So I selected this. And now can you all see the part number, operator, and then the data? Some numerical data, which because we need GAGE R&R numerical data. So all the 90 data is available. Now we are going to calculate the GAGE R&R and figure out whether the measurement system is acceptable or not. So how to do it? Go to stat, go to quality tools, go to GAGE study, GAGE R&R study, crossed. I also told you the difference between crossed and nested. When you are going for destructive testing, where the parts cannot be common, then you have to go for nested. Now the parts can be common. Just take 10 parts. Ask everybody to use the same 10 parts, right? If you select 10 different parts for the for different operators, then only you should go for nested. Now it is crossed. And now part number in column number 1. Operator in column number 2, measurement data in column number 3, and X bar or chart. And now go to option. And now what is the range between upper spec and lower spec? If you know the spec, you have to give this. If you don't know the spec, you don't have to give it, right? So let me give some assumption because the values are in 0.5. So let me say 1 unit is the spec, 0.5 on the right side, 0.5 on the left side. The total length is here 1. Upper spec minus lower spec. Now I just give OK. Once again, I am giving OK. Now the graphs are created. 6 graphs. These graphs will allow you to figure out the root of the problem. And now you see the GAGE R&R is too high. According to the specifications, look at your GAGE R&R. Do you understand, all of you, the situation now? What is the situation if it shows like this? Come on, comment. 183% is the GAGE R&R. What is the situation now? Your car windshield is full of dirt, isn't it? You can't see the road and you can't drive the car. Highly impossible. Problem is, whatever problem that is getting projected may not even be a problem. To that extent, you have error. All of you, do you understand how much is the error here? Can you read out?
183.47.
183%. But how much allowed? Only 10%. That means this data is highly contaminated with the error. So now let me copy this data. Whatever is the data, we need some data. In fact, we can create our own data and then the understanding will be much better. And for that, all of you have to do a lot of work. So now I'm pasting the same data here. So that at least, we get our names. So the same data has come here. Go to stat. One of you just guide me how to go. Go to stat. Then where should I
Quality
go?
tools.
Quality tools. I should
Quality
Quality
go.
tools.
Then
Then gauge study.
gauge study. Then
Then the
GAGE R&R.
crossed one. Gauge R&R crossed.
very good. So I do that. And now the part number, everything I have to give again. Otherwise, the old scheme will be there. I want the new structure. So part number available in column number 2 now. Double click. Operator available in column number 3 now. Measurement data available here. X bar R method. Option. Can I reduce this range? Because, sorry, can I increase the range? Because for a range of USL minus LSL of 1, how much was the error? 180%. Now I want to increase the tolerance. I make it 2. Now what will happen to the gauge R&R? Any guess?
It will
Increase or
reduce.
decrease?
Decrease.
Decrease. Very good. You're with me. Now I give OK. Once again, I give OK. And now we have Bhavin, Rajesh, Sagar. You can see the R chart showing the readings of Bhavin, Rajesh, Sagar. Similarly, everything will come to that. And now let us go here first. Oh, what happened? Increase the tolerance. With respect to steady variation, it has come down. With respect to the tolerance, why it has increased? Let's do it once again. Stat, quality tools, gauge steady, gauge R&R crossed. Option. I'm further increasing. Okay. Okay. So it is only reduced only by a small margin. Anyway, so the gauge R&R, we can calculate with respect to the tolerance. We can calculate with respect to the tolerance. We can calculate with respect to the variation in the data. So all of you, do you understand? There are 2 tables. The first table, I already explained it while discussing with you earlier. This table is based on variance or standard deviation.
Variation.
Variance, because variation means it can represent both. So variance, which is square of standard deviation. But there is one more table here, which we created it for a process tolerance of 3. This is based on
Standard deviation.
very good standard. This is the one we know all the rules thoroughly. So for a process tolerance of 3 units, the gauge R&R is still higher. So according to this particular process, this equipment, this measurement system is definitely an unfit measurement system. It is not capable, not adequate, right? So you can analyze. Maybe let me increase little more. Let us see whether it comes to control. So I'm giving wider tolerance now. Now it might look give some improvement. Can you see some improvement now? But still it is not okay. Do you understand, all of you? Right? Now, even now, the error has come down, but even then, it is 88%, which is intolerable with respect to the available tolerance. See, now one more thing. Let us understand the difference between this column, steady variation, and this column. Can anybody here tell me what is the difference between the terms steady variation and percentage steady variation? It is percentage steady variation and steady variation to tolerance. Any idea? Any idea what is the difference? In this column, the denominator is steady variation. In this column, the denominator is steady variation. Steady variation means the variation in your data. The variation in your data. The variation in your data, the total variation in your data is considered as the tolerance. All of you understand the total variation in your data is considered as the tolerance. For example, in your data, maximum minus minimum. What is the maximum reading that is there in your data? What is the minimum reading that is there in your data? That range is the total variation. That range is the total variation. We compare the gauge R&R value with respect to the total range. But when it comes to the, what do you call, tolerance, our range will be USL minus LSL. Do you understand the difference? If you give USL, LSL, then the real customer tolerance is considered as the reference. If you don't give USL, LSL, MINITAB will assume the maximum value in your data as USL and minimum value in your data as LSL, and then it will create the report. That is why you have two columns. All of you now, do you understand why do you have this and why do we have this? Please confirm.
Yeah, anyway, this will be within the range what we are fixing, or it will be taken by the system.
See, this column, percentage tolerance, when you declare USL, LSL, then only this column will appear. If you don't declare USL, LSL for some reason, let's say you don't know the data, right? You don't know the specification limits. Then MINITAB will simply assume the maximum value as the USL, minimum value as the LSL, and now you will be able to refer only the, what is this, the study variation column. Here only you need to read the gauge R&R. You understand all of you when to read study variation, when to read tolerance? What is the final conclusion?
So the tolerance.
Yes, if the tolerance is known, then refer to the last column. Tolerance not known, refer to the previous column, right? And this is the idea. And now in case you want to understand more why there is too much variation, you can read the graph. Only to just, understand better. I am using your names here. But however, we'll also go through the slides. Look here, first graph. What is the name of the first graph? Do you know anybody? What is the name of the graph? Is it a bar chart or
Bar
a
chart.
bar chart? So what is the difference between bar chart and Pareto?
Bar chart is having a continuous value, and Pareto is having a decremental value.
No, decremental value is correct. That is, we arrange the bars in the descending order. That is
Descending
Pareto.
order.
And in both the bar chart and the Pareto, the x-axis will be attribute data only, right? The attributes are different names, different defects and many things, right? And so this is a bar chart, and x-axis, different types of errors are indicated. Gauge R&R here, repeatability here, reproducibility here, part-to-part variation. Look at the part-to-part variation. Part-to-part variation is small, but error is too high. Do you think the measurement, it is advisable to proceed with this kind of measurement system?
No.
Definitely no. It is showing everything as a big, it will show everything as a big problem. Even if there is no problem here, even if I eliminate all the part-to-part variation, then also it will show, there is a big problem. But actually there is no problem. So this is what you can infer. You just compare the error against the total, actual part-to-part variation. Compare error with respect to the part-to-part variation. And now the second graph. Second graph shows the R chart operator-wise. First graph is for Bhavin, second graph is for Rajesh, third one is for Sagar. Now tell me who is more repeatable and who is having more error. Who is good and who is bad?
Rajesh is good, Sagar is bad.
Very good. So Sagar himself accepts Sagar is bad and Rajesh is good. So now what is the problem with the Sagar? Can you suggest me how can I improve Sagar now? Some idea based on so many tools you have learned, you attended the training program. And now tell me, how can I help with Sagar? I want everybody to work like Rajesh.
You want to reduce the variation?
What can I do? Particularly, where is Sagar struggling? Can I say at this point, pick up this point?
Yes, 4.
Yes or no?
Yes,
This
sir.
is
Yes, sir.
part number 6. So I probably train Sagar on part number 6 because while measuring the part number 6 I could see him struggling. His variations are too high. So I will probably train him, probably with other parts also, wherever I feel the repeatability is higher. This is how the readings of Sagar can be brought under control. Otherwise, both Bhavin and Rajesh, there is no much difference. But Rajesh found to be better. Rajesh found to be better. But however, here the points are continuously moving up 5 times. 5 of the readings are continuously moving up. What we expect is, we expect a random distribution of the data. Because what is randomness? Randomness is normal, am I right?
Yeah.
I need some yes in between. Randomness is
Yes, yes.
normal.
Yes, yes.
If there is no randomness, there is a pattern you could see, then this is something unusual. So I am not able to see any specific pattern except few things. One thing what I could observe is continuously 5 readings, Rajesh, was moving up. It was moving up, but however, it can move up also because the parts are different. So I even don't find it as a problem, right? And okay, so this is what you could understand. Now Rajesh is better, Sagar is having trouble with the repeatability error, and Bhavin is in between. So I need to bring all of them to the same line. Everybody should be like Rajesh, and then for that I would probably arrange special training to Sagar, and then also have arrange a final round of training with all the 3 together, and ultimately my repeatability error will come down. All of you, do you understand how I am actually addressing repeatability error here? Yes?
Yes.
Good. Now there is third graph, X bar chart. What was your lesson? What will you do with the X bar chart? How it is going to help you? What's the purpose of X bar chart? Come on, this we talked actually. Now I'm only trying to dive deeper. So tell me, what is the purpose, outline purpose of X bar chart?
Control.
Come again, sir? Control, because it's a control chart, X bar chart. The purpose is I'm just checking whether my product, whether my measurement system is classifying good parts as good and bad parts as bad. Good as good, bad as bad. Now, one of you tell me, what are good parts and what are bad parts? What are good parts and what are bad parts? Come on.
Product within the expected limit, that's a good part.
Okay.
Product which is not expected, not according to the expectation, that is the bad one.
Very good. So you selected 10 parts, right? Make sure certain percentage of your product samples are within the spec. Certain percentage of the samples are outside the spec. You understand? Certain percentage, let us say 50% are good, which means according to your definition, they are inside spec. And 50% are outside spec. So you fix a ratio 50-50. Because in your company, bad parts are also getting produced. If all the products are within the spec, suppose in your company, the rejections are very meager, or you expect the products to be always within spec. In that case, what will be the definition of good and bad? All the products that are produced closer to the target should be considered good. Am I right?
Yes.
But the products that are produced nearer to the specification limit, they may be inside, but nearer to the specification, they should be considered the bad parts. All of you are with me now?
Yeah.
Though it is accepted by the customer, I still consider those products as bad because they have got more variation. Am I right?
Yes.
So you need to have 2 categories. One good, other category bad. Generally, people conducting GAGE R&R study, they keep 50-50 ratio. That means 50% of the items are close to the targeted value. What is the targeted value in the metal plate example? 10 mm. Do you understand? 10 mm plus or minus 0.5. So 50% of the sample should be close to the target. Remaining 50% should be close to the specification. What is specification? 10.5 on the right side, 9.5 on the left side. Do you understand now? 5 samples are close to 10, 5 samples are close to
9.5.
and 9. In that manner, I have selected. Now I am plotting them in a control chart. Now what will happen? The proportion of the samples I selected close to the target will definitely stay inside control limit. Am I correct?
Yes.
But the proportion of the samples which I have selected close to the specification, close to the spec means anytime a customer might reject. According to me, those are bad. Definitely those points will be beyond my control limit. And those points should appear outside the control limit. Look at the X bar chart. Almost everything is inside the control limit. Do you understand?
Yeah.
If I have selected 50% good and 50% bad, but I see my measurement system is struggling to differentiate between good and bad.
So
Even it is considering bad parts as under control. No, the bad parts means your process is producing bad parts. Still your measurement system is not throwing it outside the control limit. What percentage of bad parts you mixed up? 50%. That 50% of the points should be thrown out. If that is not happening, your measurement system is not good. All of you understand?
yes.
If you make it a ratio of whatever ratio you want, you make it 50-50, 60-40, 70-30, expect a similar ratio here. Similar percentage of the point should come out of the control limit. Now, this is something part-wise graph. How many parts you selected?
10 parts.
Every part is measured by 3 people. Our Bhavin, Rajesh and Sagar. Bhavin produced the 3 reading. Rajesh produced the 3 reading. Sagar produced the 3 reading. So totally how many reading?
9 reading.
9.
These 9 readings are appearing here. All the 9 readings has come from a single product called part number 1. You understand?
Okay.
But look at the variation. This variation is the problem. The variation is too high with respect to a particular product. Can you find out which part number has too high variation?
Part number 8.
Number 8 and number 6 is little more, isn't it?
Yeah.
Number 6 and 8, your team is finding difficult to come to an agreement. Do you understand?
Yeah.
Part number 6, part number 8, even part number 4 pulls down your reproducibility. Can I say in that manner? Part number 4, part number 6, and part number 8 pulls down the reproducibility of the system. Because part number 4, your team is finding it difficult. 6 also finding it difficult. 8 also team is finding it difficult. So what will you do now? What will you do now?
You have to train them.
Train them on what kind of training? Will you give a
To
what kind of training you will give?
To reduce the variation and bring closer to the target.
A specific training to measure part number 4, 6 and 8. Because that's where the reproducibility is getting lost.
Okay.
But reproducibility is still not under control, even with the other parts. That means, you probably should also consider, training your team how to handle the other parts also. And now out of the 10.
Here can't we fix a tolerance limit like within the range of this? No, here can't we fix the tolerance limit like to understand?
See, tolerance, you already seen here in the control chart. You already seen in the range chart. But now this is a very normal graph. It can't show you the control limit and all. But here the idea is if all the 9 readings coming from same point or close to each other, it will look like a single pile of coins. Am I right? It never happened. It never happened. So the spread is the problem. The spread is the problem. So where is the, but out of the 10, in my opinion, part number 5 is little better, handled better. Am I right? 7 readings are close to each other except the 2 readings. So I want everything to appear like this. So you get an idea of which particular product is, pulling down the reproducibility. Product wise root cause we are finding out. Here, operator wise root cause we are finding out. Here, whether the measurement system is differentiating, discriminating good and bad correctly or not. And now this is box plot. So how to read the box plot? And this is interaction plot. Can you see the interaction plot completely going in a zigzag manner, crossing the red color line, crossing the blue color line, crossing the green. Everything is happening. Can you notice that?
Yes.
Poor disagreement. Poor disagreement. Poor instructions. We are telling the same instruction, but people are doing differently. That is happening. That is why the lines are intersecting. If everybody is trying to comply with the instruction given, we will see the graph at least going parallel to each other. If everybody is trying to work properly, we will see the lines parallel to each other. If they actually work properly, we'll see all the graphs overlapping. Do you get my point? If they try to work correctly, immediately the graphs will become parallel to each other, like the railway track, because anyway they are going to end the same destination. But if they are completely confused, not agreeing to each other, this kind of intersection will happen. This is called interaction. Shall we go to now the slide mode and then to gain a little more insight? Or any question to me right now with this example? Come on, black belts here.
No, sir.
Yeah. So I will stop the MINITAB. I'll take you through the slide mode now. So please confirm once the screen is visible. Visible? Screen is visible?
Yeah.
Very good. All the 6 graphs you have. So what is the first graph is giving you, telling you? Look at, can one of you read it out?
Gives broader picture of variation.
Broader picture of variation. What is the broader picture? How much is the measurement error?
Yes.
How much is the real problem we are trying to attack? Real problem should be a problem bigger than the measurement problem, isn't it? Because measurement problem with something we should control with respect to the measurement system. So this scenario is better, but not the example we have seen. And now this gives a picture of the repeatability component. This gives the picture of reproducibility component. Now this one, can one of you read this one? The R chart, purpose of R chart. Come on, read it out, one of you. Not necessarily Rajesh, the other person also. Let everyone participate. Now Bhavin, please read this. Unmute Bhavin, unmute and read. I think you are not unmuting you. Now.
Take the repeatability of
Appraiser.
appraisal.
So repeatability is important for every appraiser. First appraiser, second appraiser, third appraiser. I need a random pattern. At the same time, I want to see all the points inside the control limit. All the points inside the control limit, so no problem. It's under control only, no need to worry. But I see a unique pattern with respect to operator number 2. What is the unique pattern? Can you see all the lines appearing as a flat straight line?
Yes.
So that shouldn't be the case, right? Because everything, it's coming as what we are visualizing is we are visualizing the error, right? And error cannot be constant, but this person is projecting me as if the error is perfectly constant throughout, but it cannot happen. So in that sense, I even doubt this particular readings. Probably the person is biased, or probably the person has, got some fear. So he is trying to, replicate his reading. So that's the reason why the error is, remains constant. Otherwise, it cannot remain constant. Am I right? With actual reading, error will fluctuate. So somehow you can understand, and I could also understand here the operator 1, the repeatability is little poor compared to 2 and 3. But 2 has the problem of creating a pattern. So this is what you could understand. And now the third one. And now can one other person read the purpose of the third graph? Purpose of the third graph.
Check the ability of measuring system to differentiate good or bad.
Ability of the measurement system to differentiate between good and bad. That's all. Because I purposely mixed bad parts into the good parts. Good parts are the parts which are close to the target. Bad parts are the parts which are close to the spec. The average of my readings are plotted here. And the average of the bad parts should fall beyond control limit. That should happen. If that is not happening, that will be a problem. And now the fourth graph, response by part. 10 parts, every part, there are about 9 readings. It checks the part-wise reproducibility. It checks the part-wise reproducibility, not operator-wise reproducibility. Part-wise reproducibility. It checks the overall reproducibility. And this checks whether any specific part, any specific appraiser is affecting the measurement, which means I am doing very well. But specific part number, I struggle. I teach all the topics very well, but specific topic, I'm struggling to teach. That means that topic has got some influence in my ability to teach. Do you get my point? Similarly, the product that you are currently measuring has got some ability to disturb you. So you should equip you little more to handle such parts, right? So these are the things. Now let us go further deeper. Now the bar chart. There are 3 color graphs. Am I right? The blue color, red color, yellow color. The blue color is the one which you can use when you work based on the variance. You remember in the GAGE R&R report, there are 2 types of table, right? The first table is based on variance. Second table is based on standard deviation. If it is variance, you are supposed to refer only the blue color. If it is standard deviation, you can refer to red or refer to yellow. If you give the tolerance, if you know the specification limit, you can use yellow bar. If you don't know the tolerance, you should use only red bar. All of you, do you understand the purpose of 3 colors? If the tolerance is given by me, known to me, which color will be very apt for me now?
Yellow.
So I am removing the remaining 2. I'm removing the remaining 2. I don't want to get confused too much. Only the 3, the yellow color. And now calculate. It means calculation is based on standard deviation, and the USL, LSL values are known to me. I am comparing the error with respect to the tolerance, which is USL minus LSL. Now tell me, which is dominating? Measurement error is dominating, or the real problem is dominating?
Measurement error.
Measurement error, do you think measurement error is more than the real problem? Real problem is this one. Measurement error is this one. Which one is bigger?
Real problem.
Real problem is bigger. That's how the situation should be always. Right? When I am trying to solve a problem, I should have a measurement system which has less variation compared to the part-to-part variation. So that is okay here. But even then, the percentage wise, it is not good. The percentage wise, it is not good. Right? So 30-40% is there. We know 30-40% is unacceptable. Okay, I want to control. Now tell me which one I should control first, repeatability or reproducibility?
Repeatability.
I'm wondering why others are not trying with the answer. You still feel, not confident even after going through, proper foundation. You need to start practicing. Otherwise, it will never come, right? It's a simple visualization. Repeatability should be your first focus because it is more intense than the reproducibility. Attack this first and then come to the reproducibility. Both you need to attack, I agree. But the order of preference is repeatability first and the reproducibility next. All of you, do you understand the first graph?
Yes.
Now we move on to second graph. What is the purpose of the graph? What is the purpose of the graph now? We check the repeatability of the individual appraiser. Whether the repeatability error is under control or not. It looks under control, but my data says still the repeatability is more. I want to reduce it. If I have to reduce it, now I will probably work with certain points. For example, this point number 2, I don't like the readings. The operator 2, while working with part number 2, I don't like. Similarly, part number 10 here, part number 5 and 4 here. I want the points to be close to the center line, and I don't want to see any kind of pattern. Right? Because pattern is something unusual. And randomness is preferred, and less variation is preferred. So I think all of you will be able to handle this graph and take appropriate decision. And now here, you all know here the purpose is whether the system can differentiate between good and bad. 50-50, if you consider mixing ratio as 50-50, 50% of the points should come out of the control limit. Can you all see points coming out of the control limit here?
Yes.
Yes, sir.
That means your system has got a good resolution. Now, out of the 9 people who are attending the meeting, 3 of us are on the video. 6 of us are not on the video. My eye has got a capacity to differentiate between those who are on the video and those who are not on the video. If someone, 90 plus age is sitting here, he may not be able to do it, isn't it? So this actually tells the discriminating power of your measurement system between the categories. The category can be good and bad, or you can even, come out with multiple category and try to see whether your system can recognize all the category. This is what we are checking in terms of NDC. What is NDC? Number of distinct data categories. What is the requirement? NDC should be minimum 5. NDC should be minimum 5. If you only check position of control limit and whether the points are inside, outside, they are only checking good and bad. But you can have 5 different lines and expect the points to fall according to the categorization you have done. Now, what is this graph? Purpose of the graph? What is the purpose of the graph? Repeatability or reproducibility, or what is the purpose here?
So check the
Part-wise reproducibility.
reproduce.
Part-wise reproducibility. Tell me which particular part your team has handled in the best manner. Which particular part your team has handled in the best manner?
8.
8 or 7?
8 only.
8 is here. The spread is more. 7 is here. Spread is less.
Okay.
6 is
I
here.
got
Spread
it.
is less. 6 and
Got it.
7, your team handled better. But what is the part your team has handled in a worst manner?
10.
10.
The
10
last
number.
day, the last session, the attendance is very poor. Something like that, right? So, the part number 10, there is a lot of variation, lot of spread. So, where to focus? You get a clear idea. You keep some important thing on the last day, last session. You keep reserve some important announcement on last day, last session, and tell them in advance so that the problem can come down. Same way, think about what can be done so that your team can work effectively on part number 10. And now, coming here, this graph is called a box plot. This graph is called a box plot. Do you remember I advised you to keep your data normal? Am I right? You selected 10 parts, 5 on the right side, 5 on the left side.
Yeah.
In a perfect normal distribution, mean will be equal to median. Mean will be equal to median and will be equal to mode. Or otherwise, in a perfect normal distribution, mean will be equal to median. Mean will be equal to median. You all know the difference between mean and median? Mean is average. Median is? Center. Very good. A point that divides your area into exact 2 pieces. Right? An average is sum all the points and divide by the number of points. In a normal distribution, mean will be equal to median. Now see here, in a box plot, you see there is a crossbar, you see there is also a horizontal line. The horizontal line is median, the crossbar is mean. If your data is normal, what is the condition to be fulfilled? Mean equal to?
Median.
Median. Where it is getting fulfilled, 1 or 2 or 3?
Operator 2.
Operator 2 is correct. You make sure 1 and 3 align with 2. 1 and 3 align with 2. If 1 and 3 align with the 2, what will happen? All the mean will lie in a perfect straight line. All the mean will lie in a perfect straight line, and the mean and median will also lie perfectly. Please understand, if the people don't commit repeatability error, don't commit reproducibility error, this box plot will appear like, all the 3 mean at the same horizontal level. And the mean and median will appear at the same point. How do I tell all these things in advance? Because I only selected 10 parts. How many of you understand my point now? You are conducting the study, isn't it? You are checking the capability of your team, your measurement system. You are designing everything. Design it in a way that mean and median are same. Let us say there are 3 numbers, 5, 6, and 7. What is the mean here?
5.
6. What is the median here? What is the median here?
6.
That's all. It is so easy. You can set it. Select parts in a way that mean equal to median. Then only you can correctly tell operator 2 is doing better. Otherwise, you do not know who is doing better. Hope all of you understand my point. Now the last graph. This will tell whether there is interaction. And earlier I have shown a graph where there were a lot of intersection. But here there is not too much intersection. But there is some intersection happening. Can you tell me where is the intersection happening? From 1 to 2, is there intersection? 1 to 2? Green is
Yes.
intersecting with red. And 2 to 3? Green is intersecting with blue. 3 to 4? No intersection. 4 to 5? No intersection. 5 to 6? There is intersection. Blue is intersecting with green as well as red. So wherever there is an intersection, you need to understand something wrong between the part and the object. I am very good with all the topic, but really struggling at certain topic. CPCPK, I don't understand. I am paying full attention. I am able to understand everything. But when a particular topic is discussed, in spite of my best efforts, I am struggling. This is what you are understanding here with the intersection. And who is actually struggling? See, red is going upward. Can all of you notice? Green is also going upward. But look at the way blue. Blue alone is doing something different. Try to make him either align with the red, align with the green, or at least, we should work with the same kind of pattern. This blue line should also go up. Lines intersecting means, the person is somehow deviating from your procedure. So that's what you could understand. This is what we call it interaction. Make sure there are no interaction. Try to get all the lines parallel to each other so that you understand the problem. If you actually attack the problem, all the lines will overlap with each other. This particular graph is nothing but overlapping of your X bar chart. You see here X bar chart. There are 3 graphs. Can you see? Graph number 1, graph number 2, graph number 3. This is the blue one. This is the green one. This is the red one. 1, 2, 3. I am just overlapping in the last graph. Can you see now? This interaction graph is nothing but overlapping of the X bar chart. All of you, can you notice that? Yes.
Yes, sir.
That's it. Now you are too good to take actions, bring down the error. Whether it is repeatability that is pulling down, whether it is reproducibility that is pulling down, whether it is the product that is pulling down, or whether it is a particular appraiser who is pulling down, and you create your own guidelines. The guidelines are keep mean equal to median. The guidelines are minimum 10 parts. The guidelines are 50% good, 50% bad. All these guidelines you should set. Only you should know. Other members who are involved in the study, the operator should not know about all these things. Do you get my point? If you let everything known to everyone, then they will simply try to give you a reading, and then your readings will not capture the problem. Our purpose now is to capture the problem. We want to know the intensity of the problem. The problem is measurement error, which should be less than 10%. Hope everyone is very clear. Am I right?
Yeah.
So we stop here.